Hello everybody, and welcome to exercise 6 on page 74 of the workbook. Let's take a minute to read this example together. So as in exercise 2 on page 72, let G be U of 13 and H be the subgroup 1, 3, and 9. And in this video, we're just going to be looking at part A of this exercise, which asks us to compute orders of elements, both in the group G, U of 13, and in the factor group G mod H. And what we're hoping is that we might notice some patterns here and maybe some relationships between the orders of those elements in these two groups. Okay, so we've got some calculating to do here. Let's start by just doing the calculating in the group G. Okay, and we're going to put the answers that we get in the first column of our table here, the order of those four elements. Okay, you might recall from exercise 2 that U13 has 12 numbers in it. Okay, it's just the positive integers from 1 through 12. Okay, and we'll start with the identity element. We already know what the order of the identity element is. It's 1. Okay, so we don't really need to do anything there. Okay, what about 2? Okay, well, the order of an element, again, is about what's the smallest positive power that we need to raise it to that would get us back to the identity. Okay, well, we can figure that out just by direct calculation. So if we take 2 squared, we're going to get 4. That's not the identity, so we'll keep going. And then 2 cubed would be the 4 that we already got times 2 again. So that's 4 times 2, which is 8. Still not the identity. Okay, 2 to the 4th. That would mean we'd be taking the 8 that we already have and multiplying by 2. That's going to give us 16 mod 13, which is 3. In our group, that's not the identity. Okay, 2 to the 5th, that's going to be the 3 that we already got times 2, which is 6. Okay, and we just have to keep going until we get to the identity. Let's see, 2 to the 6th, that would be 2 times 6, which is 12. Okay, and after a while, this gets a little old. I mean, we're raising it to a bunch of powers, and we know we're going to get the identity eventually, but it might take a really long time. So I'd like to make an observation here that simplifies the process a bit. I'm going to go ahead and write this down, and then we'll talk about it. Here's my bold claim. Okay, since the order of the element 2 must divide the order of the group that we're working in, okay, which happens to be 12, I claim that based on the calculations that we did above, it follows that the order of 2 has to be 12. Okay, now how do we know that? That's like saying that we would have to continue this string of calculations here until we take 2 to the 12th. Okay, well, think about this in terms of Lagrange's theorem. Okay, if the order of 2 is a divisor of 12, what are the possible divisors of 12? I'm going to just list them up here. 1, 2, 3, 4, 6, and 12. Notice that the calculations that we did ruled out the first 5 numbers on this list. We know that the order is not 1, 2, 3, 4, or 6, okay, because we raised 2 to all of those powers and we didn't get the identity. That means that it has to be 12. That's the only divisor that's left of 12. And so that saves us from having to do a bunch of more calculations here. We can say with confidence that we know that the order of 2 is 12, okay? All right, let's clear away a little clutter here and take a look at where we're at. So next on our list would be, oh, actually, before we do 4, I want to make another observation that simplifies things. Okay, if you jump to 7 for a minute, 7 is actually the inverse of the number 2 in this group that we're talking about. Okay, do you see why that is? Okay, because if you take 2 times 7, you get 14, and 14 mod 13 is 1. So 2 times 7 is equal to 1 in the group G. That means that 7 is the inverse of 2, and therefore it has to have the same order that 2 does. That's a theorem from an earlier chapter. Okay, so we must also have that the order of the number 7 is 12 without having to do any calculations. Just saves us a little bit of time. Okay, and now we're ready to look at 4 and see what about the order of 4. All right, so 4 squared, let's see, that's 16 mod 13 is 3. Okay, and I'm just going to go ahead and write out the rest of these calculations and ask you to confirm these. If you take 4 cubed, you can confirm that that's 12. Okay, 4 to the 4th is 9, 4 to the 5th is 10, and 4 to the 6th is 1. Okay, again, I'm leaving it to you to confirm those calculations. And so we had to go up to the 6th power before we got to the identity. That tells us that the order of 4 must be 6, okay, in this group. All right, so there are the orders of the elements in G. So we're done with half of the question, and now we want to find the order of 4 of the cosets in G mod H. Okay, so this is maybe our first chance to think about doing a calculation of an order of a coset element in a factor group. All right, and which of those 4 cosets is the identity element? That's H, right? And so just like in any group, the order of the identity element is always 1. Okay, so we know that the coset 1H is 1. We can fill that in. And then move on to 2 and see if we can figure out what the order of that is. Okay, now don't let the fact that these are cosets intimidate you. It's the same idea. We need to take the coset, 2H, and just ask ourselves, what's the smallest power that we could raise it to that would get us back to the identity element, which is H? Okay, so we'll start, okay, with 2H squared. That's going to give us 4H. Okay, that's not the identity, so we need to keep going. And then 2H cubed, let's see. That's going to be the 4H that we already calculated times 1 more 2H. Okay, now if you do that multiplication, you're going to get 8H, but, okay, let's clear a little clutter away here. Notice that 8H doesn't look exactly like our 4 coset representatives, which means that 8H must be equal to one of those 4 things. And to see which it is, we can sneak a peek back at the Cayley table that we did on page 72. So if you'll bear with me, we'll scroll back to that. Okay, 4H times 2H is actually 7H. Turns out that that coset is equivalent to 8H. Okay, so back here. Okay, this is really equal to 7H. That's not the identity, which means that we need to keep going here. Okay, what about 2H to the 4th? Okay, well, that would be taking the 7H that we got in the previous step. That was 2H cubed and then multiplying by 2H again. Okay, so that's 14H. Again, that doesn't appear on this list. It must be equal to one of those. So if we sneak a peek back at our Cayley table, I'm not going to scroll again, but you can look back on page 72 and confirm that if you take 7H times 2H, you're going to get H, which is the identity. Okay, so notice what that says. We took the coset, 2H, and raised it to the 4th power, and we got H. Therefore, that's the order of this coset. Okay, and we can fill in that entry in our table. Okay, and we can use maybe some of the same observations that we did up above here to simplify the calculations. You might notice, and this you could notice by looking back at the Cayley table, the coset 7H is the inverse of the coset 2H, because when you take 7H times 2H, you get the identity. So that means that we must have the order of 7H is also 4. Okay, without having to repeat the calculation that we did above. Okay, so that's 4. And then it looks like we've got one more entry that we need to fill in, and that's what would the order of the coset 4H be? Okay, well, 4H squared, if you look back at the Cayley table again, okay, back on page 72, you can confirm that 4H times itself is H. That's the identity. So we've just confirmed that the order of 4H is 2. Okay, we raised it to the 2nd power and we got the identity back again. Okay, and we've done all the calculations that they asked us to do in part A. In part B, we'll kind of try to pull this together, maybe make an observation, see if we notice any patterns, and then see if we can state and prove a little conjecture relating the orders of group elements with coset elements.